All right, we'll begin. It's week 2 Wednesday, and it is July 1st. So happy July. We are halfway through the year 2020, and I guess that's a good thing. And today, the topic of discussion is probability. Let me just mention a couple things. Okay, so I think you guys all know already, viewing quizzes are due Tuesday nights and Friday nights. Almost everybody is doing them, which is great. There is a handful of students who are not doing the viewing quizzes, which is, I guess, a little bit surprising to me because they're intended to just be a very easy way to get points. But if you skip them, then I think the people who are present in this lecture right now, I think pretty much everyone's doing them. We have a second quiz that will be released right after class today. I recommend you do your homework problems before starting the quiz. And that second quiz will be due on Friday, okay? Friday, 11:59 p.m. California time. And then once again, once you click that Gradescope link and it opens, the timer starts clicking or ticking. So please make sure you keep track of your own time, and if you miss, like, if you take too long, Gradescope's going to reject any submissions. So I would say, always give yourself 5 to 10 minutes at the end to get your pictures, scans, and get those uploaded. Oh, chapter 5 homework, I can post that right now. I usually keep these things hidden, so okay, it should be visible now. Chapter 5 homework, and that will be up. So yes, make sure you give yourself enough time to scan and upload the quiz. Okay, and as always, I just kind of recommend doing the homework before you do the quiz. I have posted the scores for quiz 1. You have to thank our grader. Our grader got those graded very quickly, got those turned around, and those scores have now been posted to CCLE. So you can check your scores on CCLE. And students are always asked for the distribution of scores, and I'm always a little bit hesitant to reveal it because there's a tendency to want to compare yourself to the rest of the class. But I guess it can be informative, so I'll share them. Before I reveal the distribution, I do want to say that you as a person are much more than your grades and your academic achievements. And so whether you have done well or poorly on a quiz has no bearing on who you are as a person. And this was a lesson that I had to learn kind of the hard way, in that, when I was in high school, when I did very well in as far as grades went, and I had tied a lot of my identity to my grades, and I imagine a lot of you have similar academic backgrounds. The fact that many of you attend UCLA, or have chosen to come to UCLA for summer school. I imagine a lot of you are high-performing students, and or at least in high school you got very good grades. A lot of students at UCLA were valedictorians at their own high school, and at UCLA you're surrounded by other high-performing students, and so when you start comparing yourself to your peers, it can feel bad. So I want to discourage comparison, and I want to just encourage just being proud of how you did, regardless of how you did in comparison to others. And yeah, so is there any way you can see your mistakes so you can learn what we did wrong? Yes, you can go on Gradescope. you can log into Gradescope itself, and you should be able to see which problems you got lost points on. And if you and Gradescope also has the option where if you believe the grader made a mistake, you can request a regrade. Give us time to process those regrade requests. So you might submit a regrade request and it might not get responded to for like several weeks. But you can log into Gradescope and see how you have done on that. Okay, so anyway, here is the distribution of quiz 1 scores. The median was 91. Q3 is 100, and the first quartile is a 74. All right, so so many of you did very well. Over a quarter of you got 100%. So that's that. And again, quiz 1, just these Gradescope quizzes are meant to be low stakes. Okay, they're worth a total of 3% each. Okay, so I guess all to say, if you did poorly on a quiz, don't feel bad. Okay, as far as how it's gonna affect your final grade, and even if you've done really well on the quizzes, make sure you still study for the midterm and the final, because those things weigh a lot more heavily. So so the quizzes are intended to be low stakes, where if you do make a mistake, you can learn from it and move on without feeling like it's going to significantly impact your grade. Okay. A handful of students scored less than 60 on the quiz, and to those students, I want to kind of intervene and just kind of make sure things are working out okay. And so if you scored less than 60 on the quiz, please reach out to me or the TAs, I'd say tonight, to set up an appointment for office hours where we can just kind of talk and just check in to make sure that that you're doing okay in the class. If you can look at your quiz and understand all of the mistakes that you've made, and if you can kind of think of a way where you can be better prepared for the next quiz, and especially the midterm exam, that I'll feel better. But if we're in a position where you're just feeling very lost, already at this point, then we need to talk a strategy about getting you back on track. Okay. We want to see our students succeed. We want to see every single one of them, every one of you succeed. And so, if you struggled on this very first quiz, please come talk to me or talk to one of the TAs. Okay. And again, right now is the time to change course. Okay. It's hard to believe, but this is our 4th lecture, which means we are already a third of the way through the course, because it's the end of the 2nd week, and it's a 6-week course. We're already a third of the way through the course, and so after the midterm, if you do very poorly on the midterm, I don't want to say all hope is lost, but it's going to be a little bit harder to kind of turn your ship onto the right path. So so what we want to do is we want to intervene now so that you can do well on the midterm and be on track. Okay, the week before the final is not the time to talk to me for the first time and say I need help. Right now is. Okay, so so if this is you, please reach out to me, and we'll try to we'll do our best to help you. Okay. Will the midterm be held in the same way? The midterm, no. The midterm will be multiple choice, in that the midterm's a longer exam, and so to kind of speed things up, the midterm's just going to be multiple choice on CCLE. So it's going to be taken on CCLE, and then for proctoring, I'm going to have everybody log into Zoom and turn their webcams on. And it's mostly just to kind of make sure that, I don't know, students aren't working together on the exam. I know it's a little far-fetched, but you know, the school wants you know, some sort of proctoring or something. You know, it's not necessarily, but we'll do it through Zoom. You'll just log in with your webcam, and I'll just kind of watch the webcams. I feel like that's a little bit better than, you know, there's other solutions like Respondus, which kind of lock up your computer and record video, and that kind of makes me feel a tiny bit uncomfortable. And so, you know, the Zoom, nothing's being recorded, but I'll be there to kind of just look, okay? And so that we will, so for the midterm exam, it will be a multiple choice exam on CCLE, and it will be proctored via Zoom. And that means we do have to hold the exam live. And so I'm gonna have a couple sessions, 10 a.m. and 10 p.m. California time. I think a couple students have contacted me and said those times don't work for them. And so I'll probably, so again, if 10 a.m. or 10 p.m., and that's next Friday, don't work for you, you know, let me know, and we'll try to arrange another time that works. And so that will be Friday, July 10th for their midterm exam. So that's what we have, okay? All right, so we will get started on today's actual lecture content. Or I don't know, are there any questions before I move on? No? All right, okay. Well, we'll go on. And so so today's chapter is all about probability. And so I want to kind of just back up to, I think I said this is like the most important slide in the course. This I showed you on the very first day of class. And we said, you know, the big picture ideas in statistics, and this is what I want you to walk away with when you finish the course. Even if you forget all of the procedures, the individual steps in a z-test and t-test, I can live with that. But I do want you to have kind of this big picture idea from the class, and that is we can make conclusions from observed data. You know, it's going to be more reliable than anecdotes and things like that. Data conclusions made from data, and the conclusions we're making are about populations that we can't directly observe. You know, we observe a sample of data, a small selection taken from the population, and we use that to make conclusions about the big population, which was too big for us to observe directly. And in our data, if we observe an association between variables in our data, right? So we learned about looking at correlation, and not last week, just on Monday, where we see an association between variables in our data. That could mean that there's an association between the same variables in the population, okay? And we'll get kind of stab at this idea a little bit more. But it's also possible that the observed association in the data could just be a random fluke, okay? So it's also possible that it's just randomness that makes that association appear. And so, so what we'll do is we're gonna learn probability today and next week. Chapters 5 and 6 focus on probability. The first half of chapter 7 is also related. Learning probability teaches us about randomness, and that's going to help us to decide if the data that we observed is a random fluke or not. Okay, and later on we will introduce the tools after the midterm exam. We'll introduce the tools like the confidence interval, the z-test, and the t-test, and those all produce kind of numeric values to help us make the conclusions. And so, you know, the last, after the midterm, it's going to be all focused on 0.5, and we're going to get into the details of carrying out each of these steps. But I want to make sure that that you guys have the big picture ideas behind the course, okay? And so, what we've done so far is, well, I said in the big picture in our class is that we want to make conclusions from data. And, kind of our first 4 chapters were about describing data, right? Chapters 2, 3, and 4, we described data with pictures. We described data with numeric summaries. We described relationships in our data in chapter 4. We just learned how to describe the data in the first place, which is necessary if we want to even start to talk about or describing the conclusions we want to make. And the kind of this next important idea is that we want to be able to distinguish between actual phenomena, actual kind of relationships that exist in the population, actual things that are happening, versus just things that happen by random coincidence. So a lot of times things will happen in life that are just random coincidence that doesn't actually indicate that something unusual is happening, right? And so in chapters 5, 6, and 7, and today we're covering chapter 5, we're going to cover kind of the basics of probability, and that's going to help us understand randomness, right? And you can, you get 3 chapters on probability, and I still call it the basics of probability because the truth is you can take an entire course on probability. You can actually take multiple classes and read entire textbooks solely dedicated to the subject of probability. It can get very deep. We're just going to cover the basics in our class, okay? And by understanding randomness, understanding how random things should appear, we're going to be able to quantify whether a particular outcome could have been a random occurrence or is it a non-random result, okay? And this is kind of where we are headed. And I want to kind of give us like a simple example, I guess, of where we are headed. We're not going to be able to answer this question today, but this is where we are headed, right? And so the question is the Carnival game a scam? And in general, most Carnival games are a little bit scammy. They take, whether they are actually cheating or just presenting things to, a lot of times they play little mind tricks to make you think you have a high chance of winning when in reality it's a low chance. But a carnival game involves, let's say there's a wheel that you spin and it's divided into 12 sections, okay? And half of the spaces on the wheel are marked to be lose, and then the other half will be win, and they've got different prizes, right? Maybe one of them is the large prize and a bunch of them are small prizes and things like that. And your friend plays the game several times. Your friend comes back and says, I think the game's a scam, right? I played the game 10 times and I only won a prize 3 times. Okay, if the game is fair, right? Because half of the spaces are marked lose and half are win some kind of prize, if our friend played 10 times, he should have won around 5 times out of 10, right? And so he only won 3 times, which is less than 5. And does that mean the game's a scam? Okay, the fact that he only won 3 times instead of 5 times, does that mean the game's a scam? Or is it possible that the game is actually fair, that the probability of winning is 1/2, and just by random coincidence, okay, just by random bad luck, our friend just had an unfortunate outcome where he only won 3 times out of 10. Okay, and I think we can imagine both of these scenarios being possible, right? And we probably won't be able to definitively answer this question just based on playing the game 10 times and winning only 3 times out of 10. But we can imagine either of these scenarios. One is the game is actually a scam, and therefore that's why people are winning at a lower rate than 1/2. It's also possible that the game is actually playing fair, and our friend just had a little bit of bad luck. Okay, but in order for us to kind of fully evaluate this, we've got to learn the basic rules of probability, right? And so we're going to we'll learn at least the probability rules set up for this question in chapter 6, and then we'll set it up into kind of a question that we can answer, and that's not going to come until chapter 8, but this is kind of where we get started. All right, does this idea make sense to you guys? I hope. Yeah. Okay. All right. So so let's get into some probability. All right. So these are kind of just the key topics that we're going to talk about: randomness, probability rules, conditional probabilities, maybe another bullet point for independent events, things of that nature. So so first we got to talk a little bit about randomness. Randomness or random means we cannot predict the next outcome, and that there's no pattern in the outcomes. All right. So we can't predict the next outcome. There's no pattern in the outcomes. Random is not the same thing as arbitrary. A lot of times you might hear someone say, pick a random number from 1 through 10, okay? And if I tell you to pick a random number from 1 through 10, you as a human being are not able to do this, okay? You are not able to generate random numbers. So you can pick a number arbitrarily. You can say, I feel like picking the number 3, or I feel like picking the number 7, or I feel like picking the number 5 or 1 or something like that. A lot of human decisions are arbitrary, but humans are bad at being random and identifying true randomness. So, so we have ways to devise randomness. We have random number tables. We have random, you can do like coin flips and things of that nature. But random is different from arbitrary. So randomness doesn't, at the same time, even though we can't predict the outcome and there's no pattern in outcomes, randomness doesn't mean we can't draw understanding. So in general, flipping a coin is considered to be a random event, and that we can't predict how a coin will land. We don't know if the next coin flip is going to be heads or tails, but we are able, and if we flip a coin a bunch of times, there shouldn't be any kind of pattern in what comes up heads and what comes up tails. But in the long run, we can kind of say that the coin should land heads about 1/2 of the time. So we are able to understand how it should behave in the long run, even though as far as one individual coin flip goes, it's going to be random. I wrote flipping a coin is generally considered to be random, and that's technically, it could be debated because I guess a coin is subject to the laws of physics. So if you knew exactly, like if you're going to flip a coin with your thumb, if you knew exactly how much force is being applied to the coin, and what the kind of the angular momentum is, and the kind of the properties of the coin and the air resistance and all of that, we could argue that we might be able to predict exactly how the coin should land. I think just the thing about a coin flip and is that even just the slightest change in the amount of force being applied can significantly impact how the coin will land, and therefore we often consider it to be random. Adel's asking, when something is arbitrary, can there be nothing said about the long run? Yeah, for arbitrary things, we can't really say anything about how things are going to behave in the long run. By observing things and taking many observations, we might be able to get kind of a sense of how an arbitrary, if something is arbitrary, it might still end up being slightly predictable. Okay, so you could imagine a person who makes decisions, and at the time the decisions feel a little bit arbitrary, but maybe after a many series of decisions, a pattern begins to emerge, and then you can begin to start talking about that. But that's a little bit more of like a psychology thing, and here we're going to be strictly talking about kind of pure random things. Okay, I guess there's, at a philosophical level, we can also ask, is anything truly random? Are my thoughts and decisions even my own? I mean, if you think about it, what's happening inside of your brain, it's just a bunch of electrical impulses being sent from neuron to neuron, and the words that are coming out of my mouth is just the result of this physical and chemical process happening inside of my brain. Are my thoughts my own? I like to think that that there's something other than what can be physically observed, that that we have spirit and soul and things like that. But if we're looking at things from a purely physical standpoint, I don't know. There's a little bit of anyway. Didn't mean to get into that, but we're talking about randomness here. Okay, so as far as probability goes, the concept of probability expresses how likely or how unlikely a particular outcome is, right? It's, in California, it's likely that in the summer you're going to have sunny weather, and it's unlikely that it's going to snow in the month of July. It's quite unlikely that it's going to snow in Los Angeles at any time of the year. It's not impossible. It has happened, but it's quite unlikely. And so we would assign a low probability, right? And, as far as like disasters go, I guess you could say relatively, there's a high risk of earthquake in Los Angeles. But that's high risk of earthquake is still quite low, right? In general, in any given year, we would not expect a very large earthquake. But compared to, other parts of the country, say Oklahoma, we would not, Oklahoma has a very, very low risk of earthquake. And, I don't know what's more likely, snow in Los Angeles or a large earthquake in Los Angeles. I don't know. But probability will be able to express how likely or unlikely some kind of outcome is. All right. We want to be able to distinguish between theoretic and empirical probabilities. They're both important. And so let me just talk about these a little bit. So theoretic probabilities, and this is what today's chapter is mostly going to focus on as far as the math and the calculations go. We're going to learn about theoretic probabilities. Theoretic probabilities are long-run relative frequencies, meaning long run, it approaches kind of infinity. So it's the idea that if you took a coin and you flipped it infinitely many times, that in the long run, the proportion of heads, okay, the relative frequency of heads, the proportion of heads you get would be 0.5. We use mathematical rules to find theoretic probabilities. And so as far as flipping a coin goes, the calculation looks something like this, right? A coin has two sides, and we're going to say each side has an equal chance of landing, and therefore the theoretic probability that a coin lands heads is 1 out of 2. There's two sides, and heads is one of the sides. So its probability of landing heads is 1/2, or 0.5. Okay, so that's a theoretic probability. And that's what we're going to focus on today. Empirical probabilities, on the other hand, these are estimates. These are estimated probabilities based on actual observations or from experiments, or even, I guess, even a simulation, okay? And these are useful to kind of estimate the probability when the math to get a theoretic probability does not exist. All right, so we would not do an empirical probability for a coin flip, but we could if we wanted to, right? And so if you were an alien from another planet, you've never seen a coin before, you have no idea how this thing works, and you're not sure the probability that a coin will land heads, what you can do is you can try flipping it like 50 times, right? You flip the coin 50 times and you record how many times it lands heads. Maybe it lands heads 23 times out of 50. And therefore, you now have an estimate of the probability it lands heads. It's an empirical probability, and you'd say, I estimate that the probability a coin lands heads is something around 23 out of 50, around 46%, okay? That's the empirical probability. More kind of a more common example or usage of empirical probability, and we use empirical probabilities very often, would be something like, what's the probability that a certain medical treatment, will be successful for this particular patient, okay? And, the idea of doing a long run relative frequency is not possible for this one patient. You only have one patient, and it's either going to be successful or it's not, and you can't repeat this experiment infinitely many times, right? But we might be able to estimate the probability of the treatment being successful by looking at past data, right? And so maybe the same medical treatment has been performed on other patients, and hopefully we can find data where other patients had a similar condition and had similar background demographics. So like, if the person you're talking about is a 65-year-old male, hopefully you can compare and see how successful it was on other 65-year-old males, right? If the process was successful on, 20-year-old females, but rarely successful on 65-year-old males, then this is not going to be good data. But hopefully we can find people in the data, in the archives, similar background demographics, similar conditions, and maybe we find 100 cases where of other 60 to 70-year-old males or whatever with the same condition, and it was successful 80 times out of 100, right? And so in that case, our empirical probability, and it's just an estimate, but based on the past data, our empirical probability is something around 0.8, okay? And so this is kind of the notion that we use in many situations where we are not able to do any kind of math, right? We don't have math that exists for saying like, oh, plug in how old the person is and plug in their demographics and plug in all of this stuff, and then boom, you get out a number, okay? A lot of times we don't have that kind of stuff does not exist. So for that, we do empirical probabilities. Empirical probabilities also are used to kind of predict, outcomes of sporting events. So anytime there's a major sporting event, the Super Bowl or the, NBA championship, which I don't know, we'll see what happens in Florida. And, there's going to be a bunch of people in like in Vegas, like the bookies that create odds and allow you to place bets, and they're all kind of estimating these things. They've got some math going on, but there's a lot of empirical stuff going on there. Okay, there is a connection between these two, the theoretic and the empirical, and we said the theoretic probabilities are based on long-run relative frequencies. Empirical probabilities are also based on relative frequencies, but they're from observations, and obviously in our lifetimes we're not able to do an infinite amount, right? We're only able to do just a set amount, a finite amount. It might be a big number, but it's not going to be infinite. And there's this concept called the law of large numbers, and it says that as you perform more and more of these real-life trials, okay, then your empirical probability, your observed relative frequency for your number of trials is going to approach the theoretic probability, okay? So, when you flip a coin 10 times, you might get 6 heads, 4 tails, okay? Your empirical probability is 0.6. As you flip the coin more and more and more times, we would expect the relative frequency of heads to get closer and closer and closer to the theoretic probability of 0.5 in the long run, okay? That's how, I have not given out the first quiz already. Don't worry, I will give that. Let me finish my slide here, okay? This is what keeps casinos and insurance companies in business. So, you know, all the casinos, they're not hiding this fact, is that all of the casinos, the games are designed to give the casino a slight advantage, right? So you play roulette, you have about, you know, you play $1 and your expected win rate is around 96%, okay, or 95%. I forget the exact number. You know, you're going to win 18 out of 38 times, type of thing. If you bet on red, or something, you know, you play craps where you roll the dice. You know, you're expected to win a certain proportion, and so in the long run, the casino is going to win, you know, about, you know, a certain percentage of the money that's being bet. Okay. Now you'd think, well, why would anybody want to go to the casino in the first place? Okay, because in the long run, the casino is going to make money, but in the short run, right? You can play 5 games, and the individual could come out ahead. The individual could win, right? In the short run, because there's variation, it's quite possible that someone gets a quote unquote lucky streak in that, you know, they bet $100 and they walk away with 1,000. That could happen in the short run. In the long run, if somebody plays, you know, hundreds or thousands of dollars in the long run, the casino is going to make money in the long run. And so so that's how it works. Insurance companies work kind of on the opposite scenario. They have actuaries that, you know, study the probabilities, and they give out, they figure out how much they should charge for premiums and how much, you know, they're going to expect to pay out. Okay, so anyway, that's the law of large numbers, that just in the long run, the empirical values should match up with the theoretic ones. All right, I will go ahead and give you your first quiz answer, and that is B as in bear, or B as in boy, B as in ball. Those are going to be, that's going to be your first quiz answer. All right, so now we're going to look at finding some rules, or looking at the rules for finding theoretic probabilities. And so we'll just start with the very basics, okay? And so we're often going to talk about some event that we designate with a letter, okay? So we might say there's some event A, and we're going to say the probability of A is written as P of A. Sometimes you'll see PR for probability of A, okay? Either of these are fine, okay? P of A or probability of A. If A is the event that a coin lands heads, we can write probability of A is equal to 0.5. Or we can write probability of heads is equal to 1/2. Okay, so these two things are equivalent, right? Now, it's important, okay? It's important that you do not say A equals 0.5, all right? So when we're talking about probabilities, don't say A equals 0.5, okay, or A is 0.5. It's the probability of the event is 0.5, okay? A itself is the event. The event is not 0.5. The probability of the event is 0.5, okay? So you must say probability of the event is 0.5 and not that the event is 0.5. Okay, basic rules. The probabilities are always between 0 and 1, 0 and 1 inclusive. So, and probabilities, we can express them as fractions, decimals, or percentages, and we use them interchangeably. So a lot of times you'll see me write probability is 0.5, I'll say probability is 50%, probability is 1/2. All of those things, those are all valid ways of expressing probabilities. Okay, if the probability is 0, it means event X is never going to happen. Okay, means it's impossible. If the probability of an event X is 1, it means X is certain to happen. It always happens, okay? And everything else is something in between. Now, a high probability, if the probability is not 1, that means it doesn't necessarily happen, right? So you might hear something like, there's a 90% chance that this is going to happen, right? There's a 90% chance of rain tomorrow or something, okay? And then it doesn't rain, all right? What does that mean? Does that mean we were wrong? No, it means that we were one of the 10% of cases, right? There's still a 10% chance of the thing not happening. And I think there's, unless you're well immersed in a lot of probabilistic situations, I think people have a bad sense of understanding of how often these, quote, low probability events happen, right? So if something has around a 10% chance of happening and a 90% chance of it doesn't happen, people are kind of relying on the 90%. But that 10% actually happens quite a bit. It happens 10% of the time, which I think is, you know, I think people are surprised, right? You can say something is going to happen 99% of the time, okay? And if we say, oh, this happens 99% of the time, it almost feels like a sure bet, okay? But we would, but that 1% is actually a much higher risk than a lot of people are willing to tolerate, you know? If airline flights had a 99% chance of landing safely, okay, we would hear about multiple plane crashes every single day, because there's hundreds of flights every single day. So a 99% probability of success is absolutely unacceptable in the airline industry. It's got to be, it's closer to, you know, 1 in, you know, several thousand, okay? And it's got, it has to be a very, very, very low risk, okay? Much, much, much lower than 1% for it to be acceptable, okay? So I think as humans, we have, when we hear something like 99%, it feels like, oh, it should be guaranteed. But 1% actually can be a lot higher than we might anticipate. Okay, the complement of an event is the outcome where that event does not happen, okay? And we can write the complement using AC for A complement, or we can just write not A, all right? So if A is like the outcome that the coin lands heads, then the complement would be the coin does not land heads, okay? And that includes all possible outcomes where the coin doesn't land heads, such as the coin lands tails, the coin rolls away, the coin lands on its side, I don't know, whatever else is possible when you flip a coin. Now, for simplicity, we might say, let's ignore these outcomes. We're going to ignore the possibility that the coin rolls away, or we're going to ignore the outcome that the coin lands on its side, and things like that. And we're going to say that if it doesn't land heads, it means it lands tails, okay? We can say that. But, you know, we're simplifying the world when we do that, okay? And so anyway, the probability of the complement, probability of A complement, is equal to 1 minus the probability of A, okay? So if there's a 80% chance of success, then there's going to be a 20% chance of something failing, okay? Or not success. That's the complement. I'm just kind of flipping through a bunch of these rules, and then we'll do some examples here. All right, there's going to be, in some situations, you have equally likely outcomes, okay? This does not apply to all situations, okay? But in some situations, we have equally likely outcomes. And if that's the case, then the probability of some event A is going to equal to the number of outcomes in A divided by the number of all possible outcomes. So if we're talking about rolling a die, Okay, there's 6 sides. Each side is equally likely. We can say, what's the probability of getting an even number, right? Out of the 6 numbers, 3 of them are even. The probability of getting an even number would be 1/2, 3 out of 6. 3 out of 6 or 1/2, 0.5. Okay, so here's just a simple example. If we have a cup full of, with some M&M candies in it, right? Let's say there's 168 pieces of candy in here, and we have bothered counting them all out. We can say 30 are brown, 25 are red, 28 are yellow, 28 are orange, 26 are yellow, 32 are green, and 27 are blue. So we've gone through the trouble of counting all of these out. We dump them in a cup, we shake up the cup, and we pick one piece of candy at random, okay? We can say, what's the probability of selecting a brown M&M candy, okay? So in this scenario, when we shake up the cup, every single candy in that cup has an equal chance of being selected, okay? And that means the probability of brown is going to be 30 divided by 168. Okay, 30 divided by 168, and that gives us around a 17–18% probability of being selected, okay, of selecting a brown piece of candy. Simple enough, okay? If we say, what's the probability of selecting M&M that is not brown, we do 1 minus that quantity, 1 minus 30 over 168, and we get something around 82%. Okay, and so all we're doing is we're just saying how many pieces fit this criteria, being brown out of total number of pieces. Okay, I think that's pretty straightforward. All right, so here is, here's a table, a two-way table that we can do, right? And then we can start kind of combining events using the word and. All right, so an event belonging to A and B has to belong to both event A and event B, right? So here in this table, we have 208 people, all right? And we're gonna say, if we select one person at random, one out of these 208 people, what's the probability that the person is from California and is a first-year student, right? So how many people fit both the criteria of California and first-year student? It's just this group here, right? So we have a bunch of people from California, 120 in total, and some are first year, second year, third year, or fourth years. And then how many people are first-year students? We have a total of 70. 30 are not from California, but 40 are from California. So the only group of people that fit both California and first-year student is this 40. So our answer is going to be 40 divided by 208. Okay, so our answer is 40 divided by 208, and we get something around 19%. Okay, 0.1923. All right, if we use the word or, okay, then it has to belong to A or B or both, okay? The or in statistics is always an inclusive or. There's a little bit of ambiguity in our English language, and actually in a lot of languages, there's ambiguity in that we use the same word for both the inclusive or and the exclusive or, okay? And in statistics, it's always the inclusive or, right? The exclusive or means you have a choice and you have to choose this thing or this thing, okay? And you can't choose both of them. But the inclusive or is kind of the and or. It's this or both, right? So I could ask, hey, do you like chocolate or vanilla ice cream? That's what we got. Are you going to be happy with that? Do you like chocolate or vanilla ice cream? And your answer there is going to be yes, or maybe not, or maybe no, okay? So, so if you like either of those ice creams, you're going to say, yes, that sounds good to me, okay? The exclusive OR is, you know, which do you prefer? Do you like chocolate or vanilla ice cream? And then you'd say, oh, I like chocolate ice cream, or I prefer vanilla ice cream or something. That's the exclusive OR. So there's ambiguity when we use the word or, but in statistics, OR is always going to be the inclusive OR, okay? So if we ask the question, what's the probability that the person is from California or is a first-year student, okay? There's a lot of people that fit this criterion. We're going to include everyone who's from California. There's a total of 120 people there. We're going to include everyone from California. And we're going to include all the first-year students. So everybody who fits kind of both is going to be, we've got these people. They're California first years, second years, third years from California, and fourth years from California. So I'm going to do 40 plus 55 plus 20 plus 5. And we're also going to pick the first years that are not from California. They also satisfy. Okay, so all the people from California or first year or both, we're going to have a total of 150 people. All right, and so that probability, that proportion, 150 over 208, is something around 72%. Okay, and so that's going to be the OR. It's always an inclusive OR. This, you can calculate the OR probability of A or B, can also be found using the probability of A plus the probability of B minus the probability of A and B, right? And so here's kind of a picture that that I drew here, is that this circle represents A, this circle represents B, okay? And so we can take the probability of A, which is this entire circle, and we can take the probability of B, which is this entire circle, but when you do that, we have double counted the overlap, right? We've double counted this green football shape, and so we want to subtract that out, right? So we're going to take the probability of A plus the probability of B minus the overlap, because we basically just want to add the moon-shaped part here. We don't want to actually add the green part here. So we're going to do the so we subtract this off here. So that's the A or B. And so this this question we can also answer using the same formula, right? So we could say, what's the probability that the person's from California or is a first year? We can take everyone from California, where there's 120 of them, and we can take all the first year students, which is, and there's 70 of them, okay? But if I do 120 plus 70, okay, this 70 is made up of this number and this number, right? We're taking this number and this number, and that's where this 70 comes from. And this 120 comes from adding up these four numbers. So we have double counted this 40, right? We've double counted the overlap. So we want to subtract one of those out. So we do 120 plus 70 minus 40. We get 150 over 208, and we get the same answer there. So that is, that's the OR probability rule. Okay. Sometimes events are what we call mutually exclusive, okay? Mutually exclusive means that the two events, they cannot happen together. So if A and B are mutually exclusive, then the probability of A and B is equal to 0, okay? The probability that A and B happen together, that's going to be 0, right? If events A and B are mutually exclusive, then when we talk about probability of A or B, right, we can simplify that to just the probability of A plus the probability of B, because this is the formula, or this is the rule for finding out the probability of A or B. Probability of A plus the probability of B minus any overlap. But if they're mutually exclusive, this overlap portion is 0. This is 0. So this just simplifies to the probability of A and the probability of B. Okay, so here's an example, right? If somebody says, what's the probability that a person is a first-year student or a second-year student? Okay, there's no overlap, right? You cannot be a first-year student and at the same time be a second-year student, okay? There's there's no situation where this occurs. You're either a first year or you're a second year or you're something else, but you cannot be both at the same time. So there's no overlap to worry about. So we can just do the probability of first year, which is 70 over 208, the probability of a second year, which is 95 over 208. We add those two together and we get 165 over 208. Okay, and that's going to be the probability of being a first year or a second year student. Okay, here's just a couple, I guess, another rules. The probability of A and B is going to be exactly equal to the probability of B and A. The order of these events here do not matter. The probability of A or B is also exactly the same as the probability of B or A. So the order of how you put these events inside the probability rule do not matter. All right, why don't we pause here? We'll pause here for, we'll say 5 minutes. We'll come back at 5 minutes after noon and being here. All right, so so we covered kind of a couple rules of probability, and now I have to introduce this this concept of conditional probabilities. All right, and so here is some new notation here. Excuse me. We'll get this vertical bar. This vertical bar has us read this as the probability of A given, this vertical bar stands for given B, okay? The probability of A given B, all right? This is the probability of event A happening, okay? It's the probability that event A happens given the fact that B happens, okay? So we're gonna say B has happened, and so this is what we want, right? So, I don't know what happened here. Okay, so here we can have probability of drives truck given from California. Okay, and we would say this is the probability that someone drives a truck if we're given the fact that the person is from California. Okay, and how does that compare to what's the probability that someone drives a truck? If we're given the fact that the person is from Texas. Okay, so I recognize maybe not everyone is from the United States, and so there's kind of a stereotype that people from Texas, that everybody in Texas drives a truck and owns a gun and things like that, and you know, loves country music, and that's probably true for a lot of Americans. But you know, California and Texas are kind of portrayed as these rival states with different political leanings and whatnot, and different things. But you know, in California there's a lot of people who drive trucks, okay? In Texas there's a lot of people who drive trucks, but we might say that there's going to be more people who drive trucks in Texas than I guess not by count, but just by you know, a greater probability that someone drives a truck if we know that they're from Texas than if they're from California, right? California, I guess the stereotypical car from California is the Prius or the Tesla or something like that. And these are just silly stereotypes. Certainly doesn't apply to everyone, but we can say, you know, what's the probability that somebody drives a truck if they're from California versus what's the probability they drive a truck from Texas if they're from Texas, right? And so these represent different kind of probabilities, different quantities, and it's conditioned, okay, based on these two different facts, that they're given that they're from Texas or given that they're from California. Okay, the way we might go about calculating this, okay, the probability of A given B is we can do the probability of A and B divided by the probability of B, okay? It can also be calculated using just counts, okay? You can do the count of A and B divided by the count of B, all right? And unlike the OR rule and the AND rules, you are not allowed to say that the probability of A given B is equal to the probability of B given A. These two things will not be equal, all right? If they're equal, it's only by some strange coincidence. This is not a rule that holds. So, so let's just try out a couple examples here, okay? So I've made up some numbers. I said, all right, let's get a survey, 2,745 people. We've got some people from California. We have some people from Texas, okay? And we have people who drive trucks and people who don't drive trucks, okay? And so if you look at the sheer numbers by itself, we might actually have more truck drivers in California, people who drive trucks. I shouldn't say truck driver, that's an occupation. People who drive like pickup trucks, okay? So things like your, Ford F-150 or the Silverado or things like that. People who drive a pickup truck, there might actually be more of them in California than there are in Texas. 470 versus 420, I'm making these numbers up because there's just a lot more people in California than there are Texas. But if you look at kind of the proportions, the relative probabilities, it might be quite different. So, so these are all different ways to kind of phrase different kinds of questions, and you should be kind of familiar with how a question might be phrased or asked if I were to put something like this on a quiz or test, okay? So here we're gonna say, let's pick a person at random from this table. There's 2,745 people. And we can ask, what is the probability that this randomly selected person drives a truck given they are from Texas? So this is the probability of driving a truck given that the person is from Texas. So when we do this, probability of truck given Texas, we are limiting ourselves only to the people from Texas. Once we say given they are from Texas, okay, our pool is no longer the 2,745 people. Once we say we know that they are from Texas, we're limiting ourselves just to this column, just to the 1,170 people from Texas, okay? And of those 1,170 people, 420 of them drive trucks. So the probability of driving a truck given they are from Texas is 420 divided by 1170, and we have around 36%, 0.359. Okay. What is the probability that a randomly selected person from California drives a truck? Okay. And so a randomly selected person from California drives a truck. This would be the probability of truck given California. So notice these questions are phrased a little bit differently, but they end up kind of having kind of the same structure here. Probability of truck given California. So given that they're from California, we have a total of 1,575 in the denominator, 470 in the numerator, and that probability is around 30%, 0.2984. Okay, so so that's what we have here. Okay, now the probability of truck given Texas is very different from the probability of Texas given truck. Okay, here we ask, what's the probability that a randomly selected person is from Texas if we know they drive a truck? Okay, so the part that is given, the given information is that we know they drive a truck. That information is given to us. Okay, so we're going to put in the denominator 890. Okay, so and then out of those 890, how many people are from Texas? We're going to say 420 divided by 890. 420 divided by 890, and we've got something around 47%, 0.4719. Right? So you can definitely expect to see questions like this appear on the quiz and on the midterm exam. And I want you to be familiar and not to get these two things mixed up. Probability of truck given Texas, don't get that mixed up with probability of Texas given truck. They are different, okay? The numerator is 420, but the denominator is different, right? In the denominator, we put probability or the count of people from Texas, 1170. Here, we're putting the count of people who drive a truck, 890. All right, so maybe I'll just pause here for a moment and just ask for your feedback and just make sure that everyone's okay with this. And if not, you know, raise your hand or give me a red X or something to let me know that something I said feels a little strange. I guess now's as good as time as any to give you your second quiz answer. Your second quiz answer today is C as in cat. C as in cat, California, car. C for the second quiz answer. Can I go back to the last slide to see the formula for probability of A given B? Yeah, absolutely. Probability of A given B is the probability of A and B divided by the probability of B. For the first question, you would only randomly select that person from the people from Texas. So the question is technically, I guess the process is we have randomly selected one person from the 2,745, okay? But I guess we ask them a series of questions or whatever, and we find out, oh, this person's from Texas, okay? And so once we find out, right, once we get this piece of information, given that they are from Texas, now we know that the person we've selected cannot be any of these 1,575 people. So once we know that they're from Texas, we know that this person cannot be any of these people from California, cannot be any of these drivers of trucks from California or these non-truck drivers from California. It has to be one of these people from Texas. So, you know, the process is, you know, we're just selecting someone at random from the original 2,745. But once we find out they're from Texas, then we're kind of limited to just this column of people. Does that kind of make sense there? Okay. All right. The first answer to the viewing quiz, sure. I normally don't like to do this, but yeah, the first answer was B, B as in bear. Okay. And again, you know, these quiz answer things, they're to kind of just encourage people to watch the lecture. You know, I don't take attendance because I know people live in different time zones and things like that, but I do want to make sure people watch the lectures and it counts for something. And so I'm doing these the lecture quizzes as a way to do that. And that's because when I took an online class, it was very easy to skip a lecture. And then once you skip a lecture, then you start this whole terrible pattern of just falling behind. And I, you know, having to, I know it's already bad enough. You have to sit through 2 hours of my lecture and then an hour, maybe even longer of discussion. And then trying to do like multiple of that in one day, that's like, it's terrible. So don't do that to yourself. All right. Just a couple more examples. All right, so if we did, what's the probability a randomly selected person drives a truck and is from Texas? Okay, so here we put in the and, truck and Texas. That's going to be 420. We got 420 people who drive a truck and are from Texas out of the 2,745 people total. And we get this number, around 15%. What's the probability that someone drives a truck or is from Texas? Okay. That's the or rule. So we're going to take everybody who drives a truck. We got 890 of them. Everybody who's from Texas, we got 1,170 of them. And then we have to subtract off the overlap. So we're going to subtract off 420. We get something around 60%, 0.5974, right? And here, if we do something like, what's the probability somebody is from Texas or from California? We just add everybody up, and that adds up to 1. All right, so this brings up an important concept known as independent events, okay? If two events are independent, that means the outcome of one event is not associated with the outcome of the other event. all right? So if events A and B are independent, then this, all three of these quantities are equal to each other. The probability of A given B is going to be the same as the probability of A given not B, which is just equal to the probability of A, all right? So the probability of A given B is just the probability of A, okay? The probability of A happening is not affected by whether B has happened or has not happened. So whether B happens or doesn't happen, the probability of A happening is just the probability of A, okay? Event B has no influence on the outcome of A, and we would say A is independent of B, all right? And if this is true, if A is independent of B, then B is independent of A. And then kind of the flip side of that is also true. If B is not independent of A, or we would say if B is dependent on A, then A is not independent of B, okay? All right, so this is a bunch of gibberish here. Let's take a look here, right? So we could ask, is driving a truck independent of being from Texas, right? So if driving a truck were independent of being from Texas, then what we would see is that the probability of driving a truck for people who are from Texas is the same as just the probability of driving a truck if the person's not from Texas, okay? So the probability of driving a truck if the person's from Texas is around 35, 36%. If they're not from Texas, okay, the probability of driving a truck if they're from, I guess, from California, 470 out of 1575, is around 30%, 0.2984, okay? So these two probabilities are different, okay? What we see is that people from California and people from Texas have different probabilities of driving a truck, and therefore driving a truck is not independent of being from Texas. They are dependent, they are related, okay? Here's a different example, all right? If being left-handed independent of wearing glasses, all right? So I just made up some numbers here, okay? So this would work out, this example works out, right? So we're gonna say if being left-handed is independent of wearing glasses, then this relationship, these two values should be equal. The probability of being left-handed for glasses wearers should be the same as the probability of being left-handed for non-glasses wearers. So what's that probability, right? So the probability of being left-handed if the person wears glasses is going to be 6 out of 60. We get around 10% probability of being left-handed. The probability of being left-handed if the person does not wear glasses, all right, we got 140 people who don't wear glasses. Left-handed people, there's 14 of them. We're going to say 14 out of 140 is 0.1. So these two probabilities are the same. We got 0.1 and 0.1. And that means people who wear glasses and people who do not wear glasses have the same probability of being left-handed, all right? So wearing glasses and being left-handed are independent, I should say are. They're independent of each other because the probability is not affected by whether someone, you know, wears glasses or does not wear glasses. Okay. So here's a few things that you've got to keep track of, right? So if A and B are independent, then probability A given B is equal to the probability of A given not B. That's going to be true. Also, probability B given A equals probability B given not A will also be true. So these are the values that we checked on the previous slide. Left-handed given glasses, left-handed given no glasses, okay? We could have also checked, all right? We could have checked probability of glasses given left-handed versus probability of glasses given not left-handed. That would have also worked, right? We could have said, what's the probability of somebody wears glasses given that they're left-handed versus what's the probability that they wear glasses given that they're not left-handed? That check could have also worked and we would have come to the same conclusion, okay? All right, but this is a common mistake I see students make, so I'm pointing it out and I'm putting it on the slide here. Do not do this check, okay? Don't check if the probability of A given B is equal to the probability of not A given B, right? So So a lot of these things look similar, and apparently it's similar enough that students get confused. These things will be different, right? So on the previous slide, it would have been, if we checked what's the probability of left-handed given glasses, is that equal to the probability of right-handed given glasses? These two numbers are definitely going to be different, right? There's just a lot more right-handed people than there are left-handed people. And so, so these things are not going to equal, and we would get different answers, but that does not mean that this is the values that we should check. Okay, this is a mistake I see a lot of students make, so don't make this mistake, is what I'm trying to say. Okay, Wiley says there has to be some random difference in those probabilities though, so to what decimal point do we say that they are the same? Okay, so yes, this is a very good point, okay? So right now, I completely contrived this example. I made up these numbers. I artificially picked these numbers so that I get exactly 0.1 here and exactly 0.1 here, right? But if we did a real survey with real people, okay, we would probably, maybe we would get like one more left-handed person. What if I get 7, okay? 7 and 13 out of 20, right? And then so suddenly I'm sorry, if I do 7 out of 60 and 13 out of 140, we're going to get slightly different numbers, right? We're not going to get 0.1 and 0.1. We're going to get slightly different numbers. And does that mean, just the fact that I got one more person or one fewer person, does that mean that suddenly left-handed and wearing glasses are no longer independent? Okay. All right. So for right now, just for this chapter, okay, we're going to just say if they're not the same, we're going to say that might mean that they're not independent, okay? This is where we're headed in the long run, is in a couple of weeks here, is that we want to be able to distinguish between, was that just is the fact that my numbers are ending up slightly different, could that just be some randomness, right? And we want to be able to distinguish that. Right now, we're just going to say, compare 6 versus 60, that's 10%. 14 out of 140, that's 10%. Hey, they're exactly the same, therefore they're independent, okay? In the future, in a couple lectures, we're going to look at these proportions and we're going to say, hey, you know what? You can actually go up to like 12%, and this can go down to 9%, and that's not different enough for us to say that they're not independent, okay? We're going to allow for randomness to take a hold. But we haven't learned that yet. So right now, we're just going to say, are they equal or not? Okay, and if they're equal, that would be an indication that they're independent. And if they're not equal, we're going to say, they might not be independent. But in the future, we're going to allow for randomness, and we're going to say, hey, we recognize that there's some randomness. So that's a very good point. We're just not there yet. Okay, but we will get there. We will get there. All right, so here's a question, okay? Let's say we've got two events, A and B, and we know that they're mutually exclusive, okay? And both of these events on their own have non-zero probabilities, okay? So A has some probability and B has some probability, and events A and B are mutually exclusive. And so here's the question. Could events A and B be independent? Could they be independent, all right? All right, and so you can answer using your participants panel. So click the participants button, or and you got your you got some buttons on the bottom, and give me your answer. Do you think yes, the events are certainly independent? No, the events are surely not independent. Or they go slower is the maybe, yes, the two events could be, but are not necessarily independent, okay? So if A and B are mutually exclusive, could events A and B be independent? Now we got a lot of people saying no, and a lot of people saying maybe. Okay, and some people saying yes, they're certainly independent. All right. Okay, all right. Well, thank you guys for participating and voting or whatever, answering, you know. All right, so the answer is no, the events are surely not independent, okay? So I'm gonna go ahead and just clear everybody's answers. So thanks for, I'm not quite sure how to do audience participation in this class, but this is an idea I had. So the answer is no, the events are surely not independent, right? So a lot of times you feel like, oh, well, why can't they, right? They might be independent, they might not be independent if they're mutually exclusive, but they're not, right? So what does mutually exclusive? Mutually exclusive means that if that A and B cannot happen together. So if B happens, then A is impossible, right? That's what it means to be mutually exclusive. If one thing happens, the other thing becomes impossible. Okay, independent means that the outcome of A is not influenced by the outcome of B, right? So if A and B are mutually exclusive, then the outcome of B actually does influence the outcome of A by making it impossible, right? If B happens, it's going to make A impossible if they're mutually exclusive, all right? And so therefore, the fact that B influences A by making A impossible means that they are not independent, okay? So A and B cannot be independent because mutually exclusive means that if one thing happens, it causes the other, maybe cause isn't the right word, but if one thing happens, we know the other is impossible. And so it does influence that outcome. It does influence that probability, which means they are not independent. Okay, I hope that makes sense there. All right. So once we have independent events, we can start doing some further calculations. And this is kind of our last section for the day. And let me give you your last quiz answer. Your last quiz answer is D. D as in dog. Okay, D as in dog for the last quiz answer, D. All right. So we're gonna have we can have sequences of independent events. So if A and B are independent, then the probability of A and B can be found by doing this multiplication, probability of A times the probability of B. This only applies if they are independent, okay? So you can't do something like this where driving a truck and being from Texas, those are not independent. You can't just multiply them together, right? You can't, but if they are independent, you are allowed to multiply the probability of A and the probability of B, okay? All right, and we can extend this, right? If we have a whole bunch of events, A, B, C, and D, and they're all independent of each other, then the probability of A and B and C and D is going to be the product of all of these things, okay? Probability of A times the probability of B times the probability of C times the probability of D is going to be the product of all of these things. So, and so you can take however many you need and so on and so forth, and this generalizes, okay? But the key is that everything has to be independent, okay? If they're not independent, this doesn't work anymore. All right, so we're going to do some example, and we're going to say we have some kind of special coin, and I don't even know if such a coin exists in real life, but we can imagine this special coin where when you flip the coin, it will land heads 70% of the time, and it will land tails 30% of the time, okay? And I'm going to say, let's flip the coin twice. Let's flip the coin 2 times. When you flip a coin, they're independent of each other, meaning, you know, how the first coin flip landed has no influence on how the next coin flip's going to land. What's the probability that the coin lands heads both times? Okay, so the answer is just the product of these two things. So the probability of getting heads both times means you have to get heads on the first flip and heads on the second flip, right? That's how we can write it. And so we can do the probability of heads on the first flip times, because the first flip and the second flip are independent, we can just multiply these two probabilities together. If they were not independent, then we can't do this, okay? So we're gonna do probability of heads on the first flip, which is 0.7, probability of heads on the second flip, which is also 0.7, and we get 0.49, okay? So what's the probability that the coin lands heads both times? We get something 49%. Okay, so here's our coin again, 70% chance of getting heads, 30% chance of getting tails. We're gonna flip the coin twice. And here's the question, what's the probability that the outcome of the second flip matches the outcome of the first flip? All right, what does that even mean? Okay, well, let's list off the possible outcomes, right? So if you flip a coin twice, you can get heads, 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 tails, tails, heads, and tails, tails, okay? And heads, tails is a different outcome from tails, heads, okay? So you could imagine a family of, this is kind of another analogy, I guess, is like a family, you know, they might have 2 children, and families with 2 children, you might have 2 girls, a girl and a boy and a girl, or 2 boys or something like that. And the outcome of having, you know, the girl be the older sibling and the boy being the younger sibling is a different outcome from the boy being the older sibling and the girl being the younger sibling. So we have to have distinctions between all these. 4 possible outcomes: heads, 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 tails, tails, heads, tails, tails. Okay, and the question is probability that the outcome of the second flip matches the outcome of the first flip, right? So the outcomes heads, heads, and tails, tails satisfy that condition, okay? And these 2 events, heads, heads, and tails, tails, are mutually exclusive, right? There's no outcome where you got heads, heads, and at the same time got tails, tails, right? When you flip a coin twice, either one of these things happened, okay? You cannot get both. So anyway, we can write this, that the second flip matches the first flip is equivalent to getting heads, heads, or tails, tails, heads, heads, or because they're mutually exclusive, we can just do the probability of heads, heads, plus the probability of tails, tails. And the probability of heads, heads, because they're independent events, is 0.7 times 0.7. And the probability of getting tails and tails is 0.3 times 0.3. We add these two, we multiply these together and we add them up, and we get 0.58. And that's going to be the answer to this question, right? So this is, so the questions get, you know, a little bit more complicated. You just have to think about, you know, what these things mean. And we go there. Do I have a typo here? Typo point. I'm sorry, I'm missing the typo here, I think. 0.3 times 0.3, I think is 0.09. Yeah. Okay, all right, so here we've got another example. All right, so we're gonna flip the coin 4 times, and we're gonna say, what is the probability that we get heads all 4 times? All right, so we're gonna get heads all 4 times. We're gonna flip the coin 4 times. So here we're gonna get heads, 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 and we just multiply all of these together. So that's gonna be 0.7 raised to the 4th power, and that becomes 0.2401. All right, I think that's rather straightforward. So 0.7 raised to the 4th power, getting heads all 4 times. Okay. We could say, what is the probability that we get heads 0 times? Okay, the probability of getting heads 0 times means that we have to get tails, 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 right? That's the only outcome where we get heads 0 times. So the probability of getting 0 heads is going to be tails, 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 and we multiply all of these together, and so that's going to be 0.3 raised to the 4th power, and that ends up being 0.0081. All right, okay, and then the last one, I think, is this my last slide? Yes, this is my last slide. The question is, what is the probability that we get heads at least one time? Okay, so we're gonna flip the coin 4 times, and we're gonna say, what's the probability that we get heads at least one time? Okay, so at least one time means we get, you know, either 1 head, 2 heads, 3 heads, or 4 heads. Okay, well, if I'm flipping it 4 times. Okay, here's the thing. In life, the complement of at least 1 is 0. So whatever we're talking about, okay, anything, the event is either going to happen 0 times or it's going to happen at least once. Okay, so whatever event you can think about, right? Either it's going to happen, it will never happen in your life, or it will happen at least one time in your life. Okay, and so they are complements of each other. 0 and at least one time are complements. So getting at least 1 head is the complement of getting 0 heads, right? So either something's going to happen 0 times, either we get 0 heads or we get at least 1, okay? Something is going to either happen never, 0 times, or it happens at least once. Those are the kind of the only 2 scenarios. They're complements of each other. And so we can say the probability of getting at least 1 head is going to be 1 minus the probability of getting 0 heads, okay? And then the probability of 0 heads we actually calculated on the earlier slide. And we can just do 1 minus 0.3 to the 4, 1 minus 0.0081, and we get 0.9919. So there's about a 99% chance of getting at least 1 head, okay? But there's also the chance that you don't get at least 1 head, okay? And that means you have to get 0 heads, and that would only happen if you get tails, 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 which is a low probability, but not impossible. Okay, how does all of this feel? I hope it feels okay. And again, if you have any questions, you throw them in the chat or whatnot. You have GradeScope Quiz 2, that's due Friday. I would recommend working through some of your homework problems before doing that. And again, if your performance on Quiz 1 you know, was around a 60 or lower, please reach out to me or one of the TAs. You know, we can set up an appointment of office hours, you know, at some other time outside of my regular office hours. I've got regular office hours at 11 on Friday, but if you want to set up an appointment at some other time, I'm happy to meet with you. I do want to get you back on track, or not. I don't want to say back on track, but I do want to get you kind of up to speed, get you ready for the midterm. Okay. Oh, we have a question. What would be the probability of getting 1 head and 1 tail? Okay, would it be 0.3 times 0.7? Okay, so that is a good question. This is a student asked, what's the probability of getting 1 head and 1 tail? And so the question is, does the order matter? If we're talking about getting tails first, followed by heads, let me pull up my, so just sketch I made. Okay, so all right, probability of 1 head and 1 tail. All right, so the way this question is phrased, to me, I feel like order does not matter. Okay, so this could be the situation where we get heads first and tails second, or tails first and heads second. Okay, so the probability of heads first and tails second would be the probability of heads times the probability of tails And then the or, because these are mutually exclusive, we would also add the probability of tails times the probability of heads, okay? So this is going to become 0.7 times 0.3 plus 0.3 times 0.7, which is going to be 0.21 plus 0.21 equals 0.42, right? So we can do, yeah, 0.21 times 2, which is 0.42, okay? Now, that's a different question from what is the probability of, you know, first heads and second is tails, okay? So it's kind of the difference between asking the question, you know, what's the probability that a family has one boy and one girl versus what's the probability that the older child is a boy and the second child is a girl, okay? There's a difference there, okay? So probability of first heads, then the sequence has to be heads first, then tails, okay? And so that's going to be 0.7 times 0.3, which will be 0.21, okay? So this concept of does order matter or does order not matter is actually going to play a big role in Monday's content. So next week, after the weekend, is we're going to look at what we call the binomial probabilities, and that's where order doesn't matter and things like that. And so we'll kind of fully explore some of these questions and ideas here. Okay, and then we got another question. What about other at least problems? Okay, so yeah, we could ask the question of what is the probability you get at least one tail, right? What's the probability of getting at least one tail? And how should we do that question? Okay, so let's just, so probability of at least one tail, okay? This is going to be equal to the complement of getting 0 tails. Okay, so probability of getting 0 tails. So this would be, we would do 1 minus the probability of 0 tails, which would be 1 minus the probability of 4 heads. And so I would do 1 minus 0.7 to the 4, 1 minus 0.2401, 0.7599. That's that. Okay, meant more like at least 2 heads for 4 flips. Okay, so that one we will not be able to answer until we do until we get into chapter 6. But yeah, we can preview this, and at least you can start thinking about it, and so, you know, what is the probability of at least 2 heads and 4 flips? Okay, and so this is going to be probability of 2 heads plus the probability of 3 heads plus the probability of 4 heads, okay? Now, this gets complicated because the probability of 2 heads has possible outcomes, right? We got heads, heads, tails, tails, heads, tails, heads, tails, heads, tails, tails, heads, and there's actually 6 of these sequences. We can have tails, tails, heads, heads, tails, heads, tails, heads, and tails, heads, heads, tails. All right, so there's 6 arrangements, and we would have to calculate all of these out. Okay, and so we'll talk about this on Monday when we do the binomial probability. So it's a good next idea that you're aware of and you're thinking about. but we'll solve all of these things. And you can also do 1 minus the probability of 0 heads and 1 minus the probability of 1 head. Yes, absolutely. That's another way of doing it, of getting 2 heads out of 4, certainly. Probability of 0 heads we can do. Probability of 1 head, we have to think of all possible arrangements, and there's going to be 4 of them. And so we will talk about that on Monday. So this is good thinking that you guys are thinking of. We haven't gotten that yet. Okay, so as far as this week's quiz and this week's homework, it's just going to cover the stuff you've seen on these slides. So don't worry about all of this extra stuff that I've done here. Yes. So you've got that. Okay, so we'll end here for today, and you guys have a discussion and lab section, later today. So good luck. Have a good weekend. Have a happy Independence Day or 4th of July. Whatever have you. So enjoy your weekend, and we will see you guys on Monday. So have a good weekend.